Good morning, all of you. So, in continuation with yesterday's lecture, today we will continue about the abrasive machining setup. Okay, so yesterday we have seen that it's a working principle, the mechanism of material removal, and we were discussing about the experimental setup. Okay, so this we have seen, and we were discussing about the this part. Okay, and already I have explained the working of this compressor and all the elements. Okay, and in detail we were discussing this. So elements of this abrasive jet machining system. Okay, so here I have mentioned some elements of this AGM system. Okay, so the question arises that what are the various elements of the AGM system. So we can see in the slide. First is the gas propulsion system is there, then abrasive feeder, this element element is there, then master chamber is there, then next is the AGM nozzle is there, okay, that is abrasive jet nozzle, and the last is the abrasive. Okay, so one by one we will discuss now. So first is the gas propulsion system. Okay, so it supplies the clean air gas, clean air dry gas to the profile abrasive particle. That means that it acts as a carrier gas, okay, for the abrasive particle, because we need to carry the abrasive particle from your mixing chamber to your that top surface of your workpiece. Okay, so for that purpose, to propel that abrasive particle, we need some gas. Okay, it may be the your air or other gas also. Okay, inlet gas also you can use. Okay, so for that purpose gas propulsion system is required to propel the abrasive particle. So this gas may be, as I have mentioned right now, the air or some other gas, which should be inert gas. Okay, so then you have the in that gas propulsion system we have this compressor also, okay, or a cylinder which is filled with the gas, because compressed air has to be filled somewhere in the reservoir. For what purpose? For that purpose you can use the cylinder. Okay, and we need to fill the compressed air. So for that purpose compressor is used. Okay, now if, as yesterday I mentioned that if you are using other gas than the air. Okay, so you can use other gases like inert gas, but those gases should be non-toxic in nature. So that care we need to take. Okay, and also that gas should be cheap and easily available. Okay, easily available, and that gas it should not have excess spreading or divergent type of nozzle. Otherwise what happens, the size of cavity that you are forming on the your workpiece, no, so it will be difficult to control that cavity shape. Okay, so while choosing the inner gas of your air, if air is there, there is no issue of other. Okay, just we need a air filter to clean that that dryer also. Okay, now this is about the your gas propulsion system. Okay, here just uh, remember that what is the purpose of this gas propulsion system? To propel or to carry the abrasive particles. Okay, and for that purpose you can use the gas. It may be inner gas or it may be air. Okay, and to increase its pressure we need a compressor, and then to clean that we need a dryer and a filter. Okay, now I was talking about the second element, that is abrasive feeder. Okay, so abrasive feeder it is the second element. So with the help of this abrasive feeder, again in that abrasive feeder we will have the, here you can see the diagram. Here we will have the abrasive feeder with the vibratory mechanism. Okay, I just mentioned here. So you can control the, using this abrasive feeder you can control the your quantity with the help quantity of your abrasive with the help of vibration. Okay, so the abrasive feeder, it is required to feed the your abrasive. Okay, and it has the your vibratory system. Okay, or vibratory mechanism. Okay, using that you can control the quantity of the abrasive to be free in the machining chamber. Okay. Then we have the third element, that is the machining chamber, that means this part. So this is the third element, machining chamber. So it is normally closed so that abrasive particle content in the environment is below harmful limit. So that care also we need to take. Okay, so this is very important. Okay, so we should always keep the machine chamber closed so that the fine abrasive particles do not spread in the environment. Otherwise they will be very harmful to the operator as well as that what are the person or people are present near to your machine chamber. Okay, so we have to close that machine chamber every time. Okay? And also there should be the vacuum or dust cleaner also is a part of this mixing chamber. Okay, so which is attached to your machine chamber. Now what is the role or what is the purpose of this vacuum dust collector or vacuum dust collector which is attached to the machine chamber? So that because that collector he can it can take dust particles. Okay, so they are collected the dust particle and they are cut out of the machining chamber also. Okay, you can put at the your bottom of your machining chamber, okay, to collect the dust particles. So that is vacuum dust collector. Okay, it is not a required, but just we should know. Then move to the next element, that is the your AGM nozzle, that is this part. Okay, so the first question arises is that what is the material of this AGM nozzle? Okay, so the material for this abrasive jet machine nozzle normally it is used is a tungsten carbide or a sapphire material. Okay, tungsten carbide or sapphire metals are used as a nozzle material. Okay, please remember tungsten carbide or sapphire. Okay, if sapphire is used in general, you can get a reasonable good life of your sapphire metal metal nozzle. Okay, that is around you will get the life of 300 hours. Okay, for that nozzle if you use sapphire metal, then the shape of uh, nozzle can be circular, it can be rectangular or other cross sectional. You can take the shape of your nozzle. Okay, it totally depends on the designer of your nozzle and the requirement of your workpiece. Okay, so what are the nozzle pressure normally it is uh, ranges between 2 kg per square centimeter to 8.5 kg per centimeter square. Okay, but the actual value to be used it depends upon your workpiece metal. Okay, that you are machining as well as the requirement of metal removed. Right. Okay, so as here we need to uh, understand the material of the nozzle. Okay, that is required the shape of the nozzle. Okay, so you can use tungsten carbide or sapphire material for your nozzle, AGM nozzle, and the shape of the nozzle you can choose circular or rectangular or cross section. It depends, totally depends on the first is the requirement of your workpiece and the second is the requirement of your designer's requirement. Okay, so that point you need to do. And the last and important element is that the abrasives. Okay, so here I have made a separate slide about this abrasive. Okay, which kind of abrasive material we can use in this agent. You can see. So actually, there are various types of abrasives which are used in the AGM. Just like I have mentioned that alumina you can use silicon carbide, then glass beads you can use sodium bicarbonate also you can use as a aluminum. Sorry, as a your abrasive material. Okay, I repeat, alumina Al2O3, then silicon carbide SiC, then glass beads sodium bicarbonate, etc. You can use as a abrasive particles in this EG machine. Now, how to select the abrasives? Okay, so the selection of right kind of abrasive particles for this EG process, it totally depends upon the workpiece metal property. Okay, it totally depends on the okay, so I was talking about the selection of the right kind of abrasive. So abrasive particle you can select depend upon your workpiece metal properties, then metal remover. But okay, that metal removers that you require as well as the what you want accuracy, no? So depend on this parameter you can select the abrasive. Okay, and in that again, whatever I have mentioned, the alumina, that is Al2O3 or sodium bicarbonate, they are normally preferred for cleaning the workpiece, for cutting, for deburring purposes. Okay, for the application of cleaning, cutting, and deburring, that time you can use Al2O3 and sodium bicarbonate as an abrasive. Okay. Now, while taking the overview of the non-conventional machining process, one student asked me the question about this. So the answer of that here I have explained. Okay. For what purpose or for what application you can use which abrasive. So Al2O3 and sodium bicarbonate you can use for the cleaning, cutting, and deburring of rest of the machining purpose. Okay, and whatever the sodium carbonate is there, sorry, sodium carbide, silicon carbide. So it is normally used for harder metal as compared to alumina. Okay, so SiC is used for the harder material. Okay, then glass beads. Okay, so glass beads are good for matte finish purpose. Okay, glass beads are good for matte finish purpose. Then what the next question arises, if that size of abrasive particle. So what size we should take? So size of abrasive particles normally used it is 10 to 15 micron size. Okay, 10 to 15 micron. So this statistic I got from that buka, and that we advanced machining processes. 10 to 15 micron size you can keep for the abrasive particle. Whatever the size, if you take the small size abrasive particle, so that are good for cleaning purposes and finishing purposes. Okay, cleaning and finishing or polishing. And if you take the large size abrasive particles, then that are good for the cutting purpose, because they are give higher material removal rate, that is MRR, as compared to the small size abrasive particles. Okay, so this point we need to take into account. Okay, then what are the reuse of the abrasive particles is there? So is this reuse of abrasive particle is normally not recommended for the simple reason that uh, because after usage of the abrasive particle once, uh, in that abrasive particle there may be the contamination of the chip particles. So these abrasive particles, they get contaminated with the material, okay, that has been removed from your workpiece, and you cannot easily remove, or that you cannot separate out the workpiece particles material. Okay, so due to that only it is not recommended to reuse the abrasive particle. What will happen that if you use, so whatever this contamination is there in the abrasive particles, and if you use that abrasive particles for the machining or the, any operation purpose, so if due to that contamination it may block your nozzle passage. Okay, and if it is able to block that nozzle passage, then whatever happen, the your nozzle will be break. Okay, and it will get damaged, and if your nozzle will be the get damaged, no, then it is very expensive to change that nozzle. So the simple solution is that no need to reuse that your abrasives. Okay, again, secondly, if the abrasive particle get contaminated with the chips, okay, removed from the raw piece metal, then what happens, the whatever the cutting ability is there, no, of your abrasive particle, so that will get reduced. Okay, and third reason is that the abrasive particles are not very expensive. Okay, so one can easily afford not to reuse the abrasive particle in the agent process. Okay, now here in this slide I was telling about the operation that is deburring. Okay, now the question arises in is that okay you may thinking that what is that deburring operation? So that question arises that deburring. Okay, what is deburring? So I hope you know that when you are drilling a hole inside any component. Okay, here I am taking the help of the one example. Okay, if you are drilling a hole inside any component, then you find that some of the material is left over there. Okay, of iron unable to now the removal of these burrs. Okay, removal of that whatever the material left over there on the top or bottom surface of your hole. So it is important to remove that matter. Okay, otherwise what happen if you put that component as it is into the sub assembly or assembly without removing the burr, then what happen? This burr will be dangerous or the fatal for the life or the due to that burr, the failure of the component may occur, and the removal of the burr to avoid the failure of that your component, you need to remove the burr. Okay, and so this removal of the burr, it is known as the deburring operation. Okay, and this process, that means that this abrasive jet motion process is very good for your deburring purpose. Okay, normally casting industries or the foundry industries, you can normally they are going for the deburring operation. For that purpose, we can use this abrasive jet motion operation. So this particular process, this abrasive jet motion process, is good for the your uh, brittle and fragile material. Okay, so here I have mentioned that type, depending on the type of work material that uh, we can be machined using this abrasive machine. So first is this process is good for the brittle and fragile material. Okay, it is not so effective or I can say not so good for the your ductile material. Okay, although it can be used for ductile material, but it will give you low material removal. Okay, please I will repeat that you can use this process for your ductile material, but it will give you lower material removal. Okay, okay, and to calculate the material removal rate uh, using the theoretic calculation, we have the different mathematical models of different kinds of work. Okay, that mathematical modeling it is not part of our syllabus. Okay, so this is a part one of the your average jet machine. Now let us discuss the second part of abrasive testing, that is what are the process parameters. Okay, how that material removal rate is going to change, okay, with respect to different process parameters. Okay, so that we are going to discuss now here. Now so as I have mentioned that it is important to understand the effect of various process parameters on the performance of abrasive process. So here I will give just a very of your parametric analysis of abrasive jet machine. Okay, parametric analysis means what are the different input parameters, okay, which will affect the your output or the processor response. Okay, so here I have shown the that parametric analysis of abrasive process. Okay, so this is called whatever the diagram I have shown on in this slide now. So this is normally it is called cause effect diagram or fishbone diagram. Okay, fishbone diagram. Okay, for this abrasive jet motion process, where in this slide you can find that what are the different parameters which really affect the response in case of process performance. So let us start from the first term, that is nozzle. Okay, if you see here, nozzle here I have mentioned that is first process parameter. Okay, in that nozzle again, the diameter of the nozzle is one of the parameter. Okay, then what what type of nozzle you are using or what type of metal you are using for the nozzle. That is again the second parameter in the nozzle. Okay, and another point is that the cross section of the nozzle, whether it is circular or it is rectangular. So this parameter of the nozzle also affect the your process, performance of your this process as they. Okay, then there is a second parameter is the mixing chamber. Okay, so in that again the length of mixing chamber, then type of the your mixing chamber, then the bore diameter uh, of your mixing chamber. Okay, so these parameters also affect the your performance. Okay, then we have the next that is workpiece parameter. So workpiece parameter means what? So in that again hardness of your workpiece, then geometrical details about your workpiece, okay, that you want to create on your workpiece. So that geometrical details are uh, some of the considerable consideration uh, parameters are these. Okay, then we have the abrasive. Okay, again this is another process parameter. Okay, if you see in that again abrasive we have the its property that is flowability, then type of abrasive are there, various types of abrasives are there, then size of abrasive, that are again very important parameters. Okay, here I have shown that type of abrasive, size of abrasive, flowability of your abrasive, then volume fraction of your abrasive. Okay, so these parameters also we need to, sorry, that in that again volume fraction. So that volume fraction of the your abrasive, which is flowing along with the air abrasive jet. So that is again the controlling parameter. Okay, as long as yeah, material removal is concerned. So also it controls the accuracy of your machining cavity. Okay, so uh, again next is the carrier medium. Okay, so carrier medium is another very important uh, parameter. Okay, which type of carrier medium you are using, whether it is air or some other gas, that like the your inner gas. Okay, so both affects your performance of process. Okay, then what is the here I have mentioned the what is the coherency of your carrier medium, and what is the pressure that which you are using it. So that part also affect the performance of process. Okay, then as a machining parameters of a process, it includes your, here I have mentioned that traverse speed. Okay, this is speed with which you are moving the your workpiece to get the different shape and the size of the cavity, just like by whatever we are feeding no our workpiece in thermal. So the, so like that we need to traverse or we need to remove move our the workpiece. So that traverse speed also the process parameter. Then we have the another that mixing ratio, then stand up distance and the pressure. So that process parameter also affect your performance of your workpiece. Okay, so if you talk about the pressure, no, so the pressure what with which the jet is coming out. So this pressure will decide the velocity of your jet. That means that it will decide your kinetic energy. That formula we know that 1/2 m square. Okay, so the pressure also important parameter. Then mixing ratio will give you how much volume of abrasive is there in the your abrasive air jet. Okay, then what is the SOD, that is stand up distance. Okay, we have already seen that the working principle. Okay, SOD and the ENTD both are same, and that is very important process parameter with which or that will decide the shape and the size of the cavity that we want to be on your workpiece. Okay, now these are the input parameters, but what are the your the how the your performance process, or especially the performance of the agent process can be evaluated. Okay, in terms of here I have mentioned the machining rate is the one of the uh, response of the your calculation of or evaluation of the performance of your process. So machining rate, that is a volumetric machining rate or mass machining rate. Okay, you can also call as a penetration rate. Okay, which will be in the terms of mm per second. Okay, then what is the depth of cavity? Okay, or depth of cut? that what is depth of cavity or curve means the whatever the slot we have made on your workpiece. So that is called curve. So the curve quality, the surface roughness. Okay, so that are the some responses or the performance parameters. Okay, and that will affect by this input parameters. Okay, so I want to highlight the what is this curve quality. So when you are cutting this any workpiece, no, then the workpiece you will cut into the, for example, two parts. So whatever you are making slot into your workpiece, so that slot you can call as a curve. Okay, then the whatever the quality of the surface after cutting that you are getting, that surface roughness, that is also the main process response is there in the terms of the this performance of the your process. Okay, so this is a performance analysis, and after knowing this performance process parameter, we should know the how this process parameters affect your performance. Okay, one by one we'll go. Now I will go only 2 minutes to draw this fishbone diagram. Okay, because this is very important. Parametric analysis it is called, as well as you can call the fishbone diagram. Okay, where you will get the which are the input parameter, the process parameter, and what are the performance characteristics of your agent process. Okay, please draw this diagram or run down this chart. Okay, before starting the next lecture, that time I will show the some actual working of this agent process. So I will have the I have some videos of this process. Okay. Effect of this process parameter on the uh, your performance. So in that performance characteristic means what? Here, which are mentioned that machining rate, depth of cut, curve quality, or surface roughness. So first, here I have mentioned that the effect of nozzle tip distance or stand-up distance (NTD or SOD) on your cavity diameter. Cavity diameter. Okay, how the NTD or SOD is affecting the shape and the size of cavity. Okay, so it is well illustrated in this particular figure. Okay, this diagram I have taken from the again average that advanced machining process by Wikigen book. Okay, so let us see here. So this is a nozzle. Okay, which I have shown here. This is a nozzle, and jet is coming over here. Okay, this is a jet is coming over here. So this distance is the NTD. Okay, whatever the firstly I have mentioned, no, that G1, G1. So that is the nozzle tip distance. Okay, first case is a G1. So now you can see here the size or the width of the cavity or the diameter of cavity. So it depends upon the cross section of your nozzle. Okay, so cross section of the nozzle I have shown by the D1. Okay, if you increase this nozzle tip distance from this G1 to G2, you can see this your that cavity diameter, that is the D2. Okay, will be the greater than this D1. Okay, that means if you increase standoff distance, the G1 to D2, definitely your cavity diameter is going to increase. That means D1 will be the greater than your, so D2 will be the greater than your D1. Okay, however, the depth beyond a certain limit will be decreased. Okay, okay. Now, if you further increase this, then you make it. That means if you increase the nozzle tip distance, that uh, this the G3. Okay, then you can see again the cavity diameter increase D3. Okay, that is greater than the D2. And if you further increase to the this D4, Okay, if you increase the nozzle tip distance up to G4, you can see this width has increased further. Okay, this width has increased further. That is D4. Okay, however, here please note that however, beyond a certain limit, if you further keep on increasing this stand of distance or nozzle tip distance, the depth to which the penetration is taking place now will keep decreasing. This depth will keep decreasing. Okay, so as the abrasive particle keeps moving further away, their kinetic energy keeps decreasing because of so many factors. Okay, so that is why the depth keeps decreasing, but width or diameter keeps increasing as the stand of that stand of distance keep increasing. Okay, so this point we need to consider. Okay, here again the same diagram I have shown the in another way. Okay, you can see now here with the help of the statistic, the same diagram I shown. Okay, firstly if you take the that stand up or nozzle tip distance as 0.75, that time the diameter of cut out of cavity diameter you will get the 0.5. Okay, the shape will be like this. Now if you further increase that nozzle tip distance up to 5 mm, then your that diameter of cut also going to increase up to 0.7 mm. Again, further increasing of this interior of the solid distance 10 mm. Then your diameter of cut, that is D, will increase up to 1.5 mm. Okay, you can see the shape of the diameter. Then again, if you increase the further nozzle tip distance up to 15 mm, then diameter of cut will increase 2 mm. Okay, you can see here. So this is the effect of nozzle tip distance on your shape and size of your cut. Okay, but remember here, if you keep increasing your nozzle tip distance, then after some limit or after certain limit, you will lose your you will lose the kinetic energy of your that average. And if you lose your kinetic energy, then the width of your cut or the depth of cut will be there, no, so that will get decreased, but diameter will go increasing. Okay, so this was about the effect of nozzle tip distance on cavity diameter. Please remember. Okay, and here most important point is that if you change the your workpiece material, so for different workpiece material, different nozzle tip distance will be there. Okay, please remember. Again, the average particles will be different. Okay, whatever I have shown the statistic, okay, it comes from the different literature review or different research paper. Okay, which is mentioned by that Aravans Mustang book. Okay, in that book also they have gone for the different case studies, different literature survey, and through that literature survey they come to one ideal condition. Okay, and that ideal condition, that means the this. Okay. Again, I will give 2 minutes to draw this diagram. Okay, you can draw uh, this diagram, no problem. Effect of nozzle tip distance on your cavity diameter, okay, or diameter of cut. And after this, we'll discuss the effect of certain process parameters on the performance of the agent. And in that, we will start with the process parameter like abrasive flow rate. Okay. Now we'll see the effect of this abrasive flow rate on the performance of your AGM process. Okay, so let us now see in this diagram. Okay, here I have shown the effect of different process parameters on the performance of AGM process. Okay, and the first is the abrasive flow rate. Now we can see here in the slide. You can see in the x-axis, x-axis you will get the abrasive flow rate, and y-axis you will get the that performance, that is the material removed rate. Okay, now you can see as abrasive flow rate is increasing, the material removed rate is uh, continuously increasing. Okay, up to the certain point, up to the certain point. Now see the here whatever the unit I have shown the diagram per minute. Okay, so as abrasive flow rate is increasing, material removal rate is increasing up to certain limit. Okay, and there is an optimum or maximum value of material removal rate we will get here. Okay, and after that it start decreasing. That material removal rate will decrease. It will increase the abrasive flow rate. Okay, now the question is that what are the reasons for this. Okay, so once there is a increase in flow rate, you will get the higher material remove rate till the maxima, that is this optimal value, and that you are obtained over here. Okay, and And if you keep increasing flow rate, the number of abrasive particles that remove the material, no, or cut the material removal rate keeps on increasing. Okay, and as a result of that, you can see material removal rate is increasing up to this maximum. Okay, as uh, once again I repeat, as you keep increasing the flow rate, that is abrasive flow rate, the number of abrasive particles that remove the material keeps on increasing, and as a result of that you can see material removal rate is increasing up to the maximum or up to this optimum value. Okay, now further if you increase, then your material removal rate is going to increase, because at a lower abrasive flow rate you will get the lower material removal rate due to less number of cutting edge or less number of abrasive particles. And if you increase flow rate, okay, again that increasing that flow rate, that means the beyond the your or greater than the your optimum value. Okay, okay, that is the beyond this value, that means the whatever I have shown the maximum point. Okay, so that time what will happen, the velocity of the jet, it get decrease, and hence if due to the decrease of the velocity, your material removal rate also going to decrease. Okay, because as we know that force that you are having of your jet, it is going to distribute it among the more number of particles, and as a result of that their velocity of your average jet get decrease. And once the velocity decreases, the material removal rate also start decreasing. This is the what you can see the beyond this line. Okay, beyond this line the material removal rate start decreasing, and you can see it may join your here also after certain limit. Okay, so this is important. Your material removal rate also going to increase, but up to certain limit. Okay, after certain limit or after that maxima, your material removal rate is going to decrease. Okay, like that, the effect of the nozzle tip distance here I have shown, the nozzle pressure mixing ratio. Okay, and then we'll going to discuss the capability and all. So that remaining point we will discuss tomorrow. Okay, now before closing the lecture, let me take the attendance. Now I request all of you, please write down your roll number in the chat box. Okay, and the time being, please draw this diagram. This diagram. कोण राहिले अजून अटेंडन्सेस? Okay. So the remaining part of this process parameters and its effect on the material that we will discuss tomorrow. Okay, and tomorrow also we'll see the uh, videos of this average jet must. So thank you very much.